Hi, everyone. I'm Ashrant Aryal. I'm an assistant professor in the Department of Construction Science at Texas A&M. My colleague Judy Hartell is here. Unfortunately, my student Yilin couldn't make it, so I'm presenting this on his behalf. You already said the title, so I'm not going to repeat it. But we wanted to work towards developing advanced real-time control in 3D printing. So, or additive construction by extrusion, or more commonly known as 3D concrete printing, right, has a lot of promise of being highly automated, very fast construction times, and very flexible design that can be constructed, and it has all of these promises, but it's quite far from reality right now. And some of the big challenges, right, especially during the printing process, is if we're not able to monitor the layers underneath and we keep printing above, it can buckle, it can collapse, and then you lose the whole print. And it's a complex problem because several factors that are related to the material itself and the print parameters, right? How fast you print, the thickness of the layers, environmental factors like temperature, humidity, all of these impact how the layers underneath cure and the quality of the print. So I'm a data scientist. I'm not a concrete expert. But for me, this is a real-time control problem, right? You have multiple factors that influence a phenomena, and if you can model it and capture it, then you can use it for real-time control. So the motivation, if we look at the literature, people have been working on this, and most of the past papers have focused on monitoring the dimension during the print, right? So it's been mostly geometric tracking. There are some papers that have also looked at tracking the robot parameter, like the print speed and things like that. What we saw was missing was temperature information, and this is potentially useful because when concrete cures, it's a exothermic reaction, right? So at least the speculation is that we should be able to tell how fast the layers underneath are curing if we are able to track the temperature. So we wanted to develop a sensor fusion system to be able to do that. So what we did was we got a FLIR Lepton. It's a very cheap thermal camera. And we got a depth sensor camera that uses structured light, and it also has a RGB camera. And basically, we created our own small setup just to see if we can combine these data together. And from the RGB and the depth data that's coming from the depth camera, we were able to create a point cloud. We can measure dimensions. This is a pretty early, we're at the pretty early stages of the project, so it's a work in progress. But we were able to get dimension measurements around with 5 mm accuracy, which is okay, but it's not great, right? Needs further improvement. The other thing that we developed was automatic alignment of the thermal and RGB data. So what we did was by taking the RGB image and the thermal image, they're looking at the same object, but they're at a slightly different angle, right? Because the two cameras are not the same camera. So we have to first calibrate and align these two images, apply some geometric transformation so that now both of the images look the same, and then you can overlap them. And RGB image processing and computer vision algorithms work very well with RGB data, but not so well with thermal images, right? So the reasoning is if we can overlap them, we can do computer vision, we can apply image processing on the RGB data, and then map the corresponding temperature data on top, right? So this is what we're able to do. And we have these processes of getting the transformed image, grayscaling. We apply some edge detection and contour detection, and we're able to automatically detect the sample. Now, this is one approach. You could do computer vision if you had a large enough training data that you can recognize 3D printed samples. But the idea is first we need to be able to detect the samples in real time and then align them with the thermal images. We did notice some issues. If there's a lot of clutter in the background, sometimes the edge detection fails and it recognizes the wrong object. If the image quality, like the exposure, camera parameters are not ideal, right? There's some problems there. But some of those can be accounted for by pre-processing, background removal, and things like that. But overall, this seems like a pretty good direction. We are yet to actually monitor a real print and see how beneficial this will be. So this is a work in progress, but hopefully some thought for if anyone is working on this area. That is all.